Hi Nithish.
Hi. How are you?
Yeah, I'm fine.
So, are you done with your major project now?
Yeah, I'm done with it. Like I have a little more work, so I will be completing within 1 month.
So, are you applying for PhD?
Yeah, I'm applying for it. Like it's really exhausting to look into the labs and their work, and like it's really exhausting.
You also need someone to tell about the labs and all, no? To get into know.
Can you explain me about your lab?
My lab.
So basically I work on supramolecular chemistry lab. So when I tell supramolecular chemistry lab, people just think about all the essential synthesis and all that organic lab. But so there is a difference between supramolecular chemistry lab and organic lab. So when you look into organic lab, there are basically two main spectrum of work. As in so one is like methodology, other one is synthetic oriented, target oriented synthesis. So if you look into the target oriented synthesis labs, as in they will have a particular natural products or any kind of molecule. So that is why their goal, and they will synthesize it. So that's all about the work. And methodology, they will find multiple routes to synthesize, multiple reactions, and their condition optimization, like that. So it's about the methodology. Supramolecular chemistry lab basically deals with the particular moiety. We use organic chemistry as the backbone to synthesize that molecule. And once our synthesis is done, we will be studying its physical properties, chemical properties, and all that. So synthesis is just 5%, we would tell 5 to 10% of our work. As long as we have synthesized, and then we will go for the studies. Studies is all that matters for us.
What precisely do you work on?
So basically our lab focuses on two major things. That is, one is supramolecular chiral architectures. So when I say architecture, it means like macrocycles. Macrocycles means just rings and cages in a three-dimensional cages, which has a cavity and all that. And there are something called mechanical interlocked molecules. Mechanical interlocked, as in sense, the two, let's say macrocycles, let's say the two rings, which are interlocked together by a mechanical bond. So this is mechanical interlocked molecules. There are multiple mechanical interlocked molecules up till now have been discovered, like catenanes, rhotoxanes, cutanes, Bohmian rings, and daisy chains, and all that comes under mechanical interlocked molecules. And we particularly focus on making it a chiral molecule. And so the second part of us is we are exploring about the non-equilibrium state molecules, as in like the machines or molecular machines which exist in non-equilibrium. That's what we focus on.
Then what kind of molecule do you use for your molecular architecture?
So in our lab we use multiple molecules like binol and porphyrins and all that. So I personally work on porphyrins. And if you look into porphyrin, biologists may know about this. So porphyrins are the core moiety in the hemoglobin and the chlorophyll and all that. And this is the main key element to give the color to the pigments. So that's why it's in the pigments. So this porphyrin, it has 4 pyrrole ring, and then it has multiple double bonds in it. So making it to absorb more light and all that, and it exists as a colored molecule. And one more thing is it has a cavity in between which can bind to the metal. So as long as it binds to any metal, it can do multiple functions, as in like it can coordinate to zinc, magnesium, iron, cobalt, nickel, palladium. It can take any metal, and if it takes a different moiety or different metal, accordingly its property also will change, and it can be used for multiple photophysical studies and all that.
Can you please exactly explain about the non-equilibrium?
So non-equilibrium, right? So if to put it in a simple terms, let's assume A to B, and B is the most stable state. So now this is the thermodynamic equilibrium state. Now if we extend it to C, and C is the lower energy state, so that means C is the thermodynamically equal state. Okay. So now, given that the activation barrier required for B to go to C is very high, that means the B molecule cannot cross over until and unless you give energy to it, right? So if it crosses over only, it will go to the most thermodynamic equilibrium state, and that is in the thermodynamic equilibrium. But here, since it can't cross over, so that is trapped there. So this state is called kinetically trapped state. So this is now existing away from the equilibrium. So this is you put non-equilibrium in other words. And if you take life forms, any life forms which all exist in the non-equilibrium state. So for us to be alive, what do you need? You have to eat, drink water and all that. So that means you are giving an energy source externally. So as long as you eat, that's when you can be alive. And that's go for every energy source here. And so all the plants and things, everything, they take energy from the sun, and then they process it for their chemical energy, right? So now this energy given from outside, it's keeping the system to stay away from the equilibrium. So to give a simple example about the system, let's say azobenzene. So azobenzene is basically, it contains the N double bond N system in both sides. Aryls are there. So now there is two forms exist here, that is trans form and the cis form. So trans is generally most stable form. There is more extended conjugation, hence it is more stable in this particular form. But when you give light, so it goes to the cis form. So now cis is not the thermodynamically stable state, but as long as you give light, it can convert to the cis form. So this is how you convert the system to a least energetically stable state with the help of external stimuli. And yeah.
Can you say me how you are how can you use your field of work for the applications for the work?
Yeah, so applications, as I mentioned earlier, so we basically work on this supramolecular chiral architecture, right? So this chiral architecture, as I say, cages. So cages particularly have a cavity in it. Okay, if you take any enzymes and all that in our body, it has a cavity and then it has a reactive site, and everything happens within the cavity. And that's why you get more yield, and then it is full conversion is happening there. So taking the example from there, so we are making a system which has a cavity. So now this is like a protected environment, and the reaction can occur inside this. So now this acts as a nanoreactor and something like that. So that is one way. And second way is basically, you know, as long as this cage encaptures something, so it has been protected from the environment, right? So you can store certain substance which is very toxic or which is very reactive, which can be stored inside the cage particular moiety, the cavity core, which can encapsulate and all this. And so other examples are like, you can segregate the toluene and xylene. It's very difficult to separate them. But if you take the cages which is very smaller in size, which can particularly bound to only toluene, that means you can separate the toluene to xylene mixture. This is all about the chiral and all other properties. And chiral property, if you see, as I mentioned earlier, that chirality, the chiral molecule, the enantiomerically pure molecule has to be synthesized. For that also you can use this particular cages. And for the equilibrium system, as basically this molecular machines, it has been awarded Nobel Prize in 2016. So basically this molecular machines can be bring into the life form, as in like, so now if you look into the human body, like there is particular moiety called kinesin. Okay, so this kinesin have a molecular motor attached to it, and so this molecular motor rotates very directionally with the help of the ATP. Okay, so when the ATP hydrolyzes, this motor rotates, and this helps the molecule to walk over the microtubule. So this molecule acts as a cargo which contains all the potassium ions and all the stimuli which is needed for the neurons to transmit and all that. So basically it carries over from one end of the neuron to the other end. Okay, and this happens because of this directionality motion, and this motion is an example of the non-equilibrium system. So if we take this in account, and if you are able to synthesize a system which exists in a non-equilibrium with a given energy source, that means you are actually mimicking a life form. And if you are able to go into this and then explore a possibility of creating life, and there are multiple key factors to create a life form, and this is one of the key factors. So when a system can exist away from equilibrium, that itself is a key characteristics of a life. And so we are just exploring the possibility of creating life.
That's really nice, especially the mimicking the life part. I have to look into it.
So if you have further doubts, you can just feel free to come and then we have a conversation. Yeah.
Thank you.